Hi, we are team number 4 and we're presenting our final report, Stenosis Simulation Phantom. This work focuses on the development of a vascular phantom especially designed to simulate arterial stenosis. In both clinical and educational contexts, vascular phantoms play a critical role. They allow for the safe, repeatable simulation of complex vascular conditions without exposing patients to any risk. Our phantom provides a hands-on tool for ultrasound training, helping users recognize hemodynamics patterns and anatomical changes associated with vascular diseases. To evaluate our phantom, we use two main ultrasound imaging. First, beam mode allows us to visualize the vessel structure and clearly detect the narrowing caused by stenosis. Second, color Doppler enables us to assess blood flow dynamics, capturing high velocity jets, turbulence, and recirculation. The purpose of this project was to create a low-cost, anatomically accurate phantom that supports ultrasound-based diagnostics and education. We also aim to explore the integration of imaging processing and the machine learning techniques into medical imaging workflows. The report is organized in several sections, starting with the design and the material selection, followed by the construction process. Then we present the ultrasound evaluation, image segmentation, and neural network classification. Finally, we analyze the results, discuss the model's limitation, and provide future recommendations.
To replicate the anatomical and acoustic behavior of a stenotic artery, we carefully select each component of the phantom based on functionality and ultrasound compatibility. The external casing was made with 3D print PLA at 15% infill. This gave us a strong structure with low porosity and safe in wet environments. To prevent leakage, we use flex tape and electrical tape. These provide reliable waterproofing and durable adhesion, protecting the phantom and the ultrasound equipment. At the critical junctions, where the tubes enter the mold, we apply bathroom-grade silicone. This material is flexible, water-resistant, and introduces minimal acoustic interference. Finally, for the healthy aorta, we use industrial tubing with a 1.2 centimeter inner diameter, which realistically simulates the size and behavior of the human abdominal aorta. To simulate the stenotic region, we inserted a second tube concentrically inside the first one, with a 0.6 centimeter inner diameter. This results in a 15% reduction, which is typically of moderate to severe stenosis. The surrounding soft tissue was molded using a mixture of 20% agarose, flour, and glycerin. This combination mimics the acoustic properties of real tissue, while increasing opacity and ultrasound scattering. For the fluid flow, we use 20% glycerin solution in water. This matches the viscosity of blood, around 4 millipascal seconds, and ensures stable Doppler signal. Finally, we place a thin plastic sheet on the top of the phantom to allow coupling with the ultrasound transducer without direct contact, preventing cross-contamination. The anatomical design focused on mimicking a segment of the abdominal aorta with a center stenosis. The healthy lumen was 1.2 centimeter in diameter, while the stenotic section was reduced to 0.6 centimeter. By positioning the stenosis in the middle of the flow path, we ensured visibility of three key flow regions during ultrasound analysis: pre-stenotic laminar flow, a high-velocity jet through the stenosis, and post-stenotic turbulence and vortex formation. The structure allowed us to realistically simulate and visualize the hemodynamic changes caused by stenosis under ultrasound. For the construction process, we began by designing the mold using CAD software and printing it with PLA at 15% infill. The tubing was carefully positioned inside the mold and sealed using silicone to ensure stability and water resistance. Next, we prepared the phantom matrix. We boiled water, dissolved agarose powder, added flour opacity, and stirred the glycerin to fine-tune the acoustic properties. Once the mixture was homogeneous, we poured it into the mold and refrigerated it for at least 3 hours to allow full gelatination. The final result was stable, reusable, and anatomical accurate phantom, ready for ultrasound evaluation in both B mode and Doppler imaging.
For the imaging protocol, we use the Siemens Acution Redwood ultrasound system, equipped with a linear array transducer. This setup provides high-resolution images, ideal for assessing the phantom's shallow structure. We apply both B mode and color Doppler during this evaluation. In B mode, we were able to clearly observe the structure of the vessel and the narrowing caused by the simulated stenosis. The lumen appearance anechoic in normal regions and visibility constricted in the stenoic zone. To simulate blood flow, we connected a peristaltic pump to circulate a 20% glycerin solution through the phantom. This fluid mimics the viscosity of the blood, allowing realistic flow visualization in Doppler mode. With color Doppler, we capture three key follow regions: laminar flow before the stenosis, a high-velocity jet through the narrow segment, and a turbulent flow pattern downstream, including vortex formation.
First, we created regions of interest through MATLAB to isolate and crop the lumen vessels. Later, with the ROIs were resized to 32 by 32 pixels and converted to grayscales. A label vector was created showing 0 for normal vascularity and 1 for stenosis. Later, we flattened the images into a 10-bit length vector and created a label dataset with the inputs. For the neural network, we built MATLAB using back and forward propagation with signal activations. The input layer has the same number of neurons as the bits of inputs. Later, we had a hidden layer with 3 neurons and an output layer with 1 neuron that use hard limit functions. For training set, we also use signal activation functions with 12,000 epochs and a learning rate of zero point 0.3. In the left, we have a raw image from the ultrasound, and on the right, we have several segmented images that we input into a neural network. In the healthy segments of color Doppler confirms a steady centralized laminar flow. The uniform color distribution suggests consistent flow velocity along the vessel walls. However, in the stenoid segments, there is a high velocity jet as a result of the constricted lumen. The high-speed flow is depicted by an intense aliasing and a marked Doppler frequency shift, illustrating the acceleration blood flow that occurs in the force through the narrow region. Downstream from the stenosis, the image captures turbulent flow. The Doppler signal shows chaotic, multidirectional flow vectors due to the vortex formation and the recirculation. This result analysis verifies that the phantom accurately simulates the structural and hemodynamic changes seen in vascular stenosis, providing a relief educational and diagnostic tool for visualization, both normal and pathological flow patterns. Being able to differentiate between the healthy artery and the narrow section caused the stenosis, as well as the velocity jets and change in flow direction in Doppler represented by color mixing.
Model results. An output layer with a hard limit activation function ultimately classifying the input as either normal or stenotic. For training, we use a learning rate of 0.3 carried out over 12,000 epochs, with the mean square error as our loss metric. The training here reveals a significant reduction in error, where MSE nearly converges to zero as the network learns to distinguish the features between normal and stenotic images. Also, the classifier achieved 100% sensitivity and specificity on the training dataset according to the confusion matrix. It's important to mention that without cross-validation, we must be cautious about potential overfitting. Future work will focus on implementing tenfold cross-validation to ensure the model's generalizability across diverse datasets. Finally, we reviewed the overall results and their implications. Our acoustic evaluations and Doppler analysis demonstrated clear visualizations of the stenotic phenomenon. Laminar flow pre-stenosis, high-velocity jets within the stenosis, and turbulent recirculated flow post-stenosis are all distinctly reproduced. The Phantom's structural design and material properties enable high fidelity in both qualitative and quantitative assessments, making it highly valuable for training, quality assurance, and preliminary research. On the data side, our neural network classifier performed flawlessly on the training data, separating the normal and stenotic images with perfect accuracy. However, we are fully aware of the inherent limitations due to the lack of external validation and the fact that the agarose matrix degrades within 2 weeks. Looking forward, we propose two main improvements. First, to explore more durable compounds such as cryogenified PBA for the Phantom. Second, to integrate robust validation techniques such as cross-validation into the machine learning pipeline, ensuring that our classifier maintains its performance and using data. In closing, this project represents an effective integration of physical modeling, ultrasound imaging, and computational analysis. It paves the way not only for enhanced clinical training tools, but also for future advancements in computer-aided diagnostic systems.
To summarize, our phantom successfully reproduced key ultrasound features of arterial stenosis, such as vessel narrowing, high velocity flow, and post-stenotic turbulence. This model provides values as teaching and simulation tool. It allows students and clinicals to explore both structural and hemodynamic changes using P-mode and Doppler imaging in a safe, controlled environment. Regarding the neural network, our MLP achieved 100% accuracy on the training set when classifying ultrasound images. While this shows promising performance, the lack of cross-validation suggests that the model may be overfitted. As a final point, we recommend improving the phantom's durability by using materials like Gel PBA and expanding the datasheet as validation process in future versions to make the system more robust for research and clinical training.